Hi, my name is Öykü and I'm a second-year maths student at Bilkent University. For my Physics 102 project, I observed how a moving magnet induces current in a coil. The experiment focuses on a classic setup, observing the current induced in a stationary copper coil by a falling bar magnet. The core objective has two elements. First, to confirm the existence of the induced current, and second, to precisely quantify the relationship between the strength of the magnetic field and the resulting voltage, or in other words, induced electromotive force. This entire phenomenon is governed by Faraday's law of induction. This law provides the quantitative link between our physical setup and the electrical output. In Faraday's law of induction, E is the voltage we measure, N is the number of turns in our copper coil, and d phi over dt is the rate of change of magnetic flux. In simple terms, this equation tells us that the larger the change in the magnetic field lines passing through the coil, and the faster that change occurs, the larger the voltage we will generate. The negative sign in Faraday's law leads us directly to Lenz's law. This principle dictates that the induced current must flow in a direction that opposes the change in magnetic flux that created it.
1. Okay, 0. 2. Tamam. Mantıklı değil.
As we can see from the multimeter in each video, we measured the electromotive force by making magnets pass through a copper coil with exactly 90 turns. In this table, we observe that increasing the number of magnets decreases the time taken to pass through the coil and therefore increases the speed. This suggests that the weight or mass of the setup is increasing with more magnets, leading to greater acceleration due to gravity, resulting in a higher speed when passing through the coil. This increase in speed means the rate of change of flux is even greater. The data shows a very strong direct relationship. As the rate of change of magnetic flux increases, the induced EMF, in other words voltage, also increases. The highest rate of change corresponds to the highest induced EMF. This directly validates the central principle of Faraday's law. The induced voltage is not determined by the strength of the magnetic field alone, but by the rate of change of magnetic flux. The first graph is the graph of number of magnets versus experimental induced EMF. Notice that the slope of the line is steeper at the beginning and then flattens out as we move from 3 to 4 magnets. In other words, the voltage increase gets smaller with each additional magnet. The second graph is the graph of rate of change of magnetic flux versus induced EMF. Notice how the data points form a nearly perfect straight line. This demonstrates a direct proportionality between our two variables. And this linearity is the exact result predicted by the physics. It proves that the voltage induced in the coil is directly proportional to the speed and the strength of the magnetic field change, which is d phi over dt. Causes of error could have been timing inaccuracies, which is a random error, or voltmeter limitations, which is a systemic error. Error in the voltmeter could have been because of calibration or sampling rate. If it's because of calibration, then the digital voltmeter used to measure the induced EMF may not be perfectly calibrated. Or if it's a sampling rate, then the peak voltage EMF is fleeting. If the voltmeter sampling rate is too slow, it might miss the true maximum voltage as the magnet passes through, resulting in a measured EMF lower than the actual value.